I want to thank the organizers for having me here. This is obviously about another slice of Maxim's work about homological mirror symmetry. More precisely, it's about a new intersection of homological mirror symmetry with representation theory. So there's a new family of mirror pairs of Calabi-Yau manifolds for which homological mirror symmetry can be understood as explicitly as in the simplest known examples. So the data that goes into defining the mirror pair will be a choice of a simply laced Lie algebra, G, a collection of its representations, and a weight in that representation. So the story has a generalization to a non-simply laced Lie algebras and also to Lie superalgebras as well. The categories involved will turn out to admit break group action. Break group action that categorifies the action that comes from quantum groups associated with G. So as an application, we will gain a new and explicit understanding of this description of categorification of quantum link invariants, a description that works uniformly with respect to the choice of a Lie algebra. So in his 94 ICM address, Maxim conjectured that the way to understand mirror symmetry is that relates a pair of Calabi-Yau manifolds is as an equivalence of categories, one of which comes from complex geometry and the other from symplectic geometry of the mirror. So the category that comes from complex geometry is the derived category of coherent sheaves supported on complex submanifolds of X. The category coming from symplectic geometry is the derived Foucault category, whose objects are supported on Lagrangian submanifolds, Y. So in the very best instances of homological mirror symmetry, one learns how to make the equivalence of categories manifest. So a simple example is to take X and Y to be a pair of infinite cylinders. In SYZ terms, they have a common base, which is a real line, and the fiber is a circle. Now, both categories are generated by a single object. Now, while the generators look different, the endomorphism algebras, once properly formulated, turn out to be the same. The proper formulation here means that on the A side, the derived Foucault category is based on the wrapped Foucault category of Y. Then the morphism algebra of the generators on both sides turn out to equal to the algebra of complex functions, of functions on a complex cylinder. So from the equality of the algebras, you turn out to get a pair of equivalences where D sub A is the derived category of modules for the algebra A. Now, so by reduction to algebra, the two geometric categories, one based on coherent sheaves on X, one based on Lagrangians on Y, become manifestly equivalent. And so this simple example is a model for how you might hope to understand homological mirror symmetry in all cases. So I'll describe a new family of homological mirror pairs where just that happens. We will be able to understand homological mirror symmetry essentially as explicitly as in this model example. So the virtue of this family that I'll describe is a deep relation to representation theory of quantum groups. And having understood homological mirror symmetry, it will turn out that we will be able to solve problems that you cannot ordinarily solve in this world of derived categories of coherent sheaves or derived Foucault categories. And so we will apply this to categorification of quantum link invariants. So to start, we'll pick a simply laced Lie algebra. The B side target space will be a very special kind of a Calabi-Yau manifold. It's a family of Calabi-Yau manifolds, which has certainly been considered by mathematicians before. They have several different descriptions. One way to describe X, the one that I'll use here, is as the moduli space of G monopoles with prescribed Dirac singularities on R3, where G here is the Lie group of adjoint type with Lie algebra we've been considering. If you view X as a modular space of monopoles, then it's parameterized in part by positions of smooth monopoles on R3, and positions of singular or Dirac monopoles are kept fixed, and they'll determine the metric. So you're studying monopoles on R3. By splitting R3 as R times C, you pick a complex structure in which the positions of singular monopoles on R are the real Kähler moduli, and then positions on C are complex structure moduli. Another way of characterizing such X is as a Coulomb branch of a three-dimensional quiver gauge theory with n equals to 4 supersymmetry, where the quiver is based on the Dynkin diagram of the Lie algebra. Yet another way that's not as general as these other two is a certain intersection of slices in a fine Grassmannian of G. And this other way has played an important role in Langlands. So it's certainly well known to mathematicians. So the manifold X now is not your typical Calabi-Yau because it has more symmetries. X is holomorphic symplectic. So we'll destroy this extra symmetry by working equivariantly with respect to C star action that scales its holomorphic symplectic form with weight Q. That Q will be the same Q of quantum groups. That symmetry comes from rotations of this complex plane in R3, again, viewing X as the modular space of monopoles. And it will be an isometry if you choose all the singular monopoles to lie at the origin of this extra complex plane. So this X has a larger torus of symmetries, which we'll call T. The category of B-type branes on X that we'll consider is the derived category of T equivariant coherent sheaves. Lambda is a part of the torus that preserves the holomorphic symplectic form and comes from the maximal torus of G. What I'll mean by the equivariant category of coherent sheaves is we'll keep track of gradings of all objects and morphisms with respect to this equivariant torus. Now, like in our model example, this category turns out to be finitely generated. Bezrukovnikov and Kaladin, using quantization and characteristic P, show that for holomorphic symplectic X that includes these in our family, they have what's a tilting vector bundle, which is a direct sum of finitely many things, which generates the category. The endomorphism algebra of the tilting vector bundle turns out to be an ordinary associative algebra that's graded only by equivariant degrees. And then, per definition, the derived category of modules for this algebra, the endomorphism algebra of the tilting bundle, is equivalent to the derived category of coherent sheaves on X. Now, this equivalence, you can view it as a generalization of one's favorite example of a category of B-type branes, where the right-hand side is a category of modules of, say, of a quiver path algebra. Now, for this family of Calabi-Yaus, the endomorphism algebra of the tilting bundle was computed explicitly by Ben Webster in 2019. He showed that the algebra A is a cylindrical version of a quiver Heck algebra. That Quiver-Hecke algebra, the cylindrical modification is a minor thing, but the Quiver-Hecke algebra was constructed by Kovanov and Lauda and by Roquier some years early in 2006. Now, the latter algebra is known as the KLR algebra or KLR-W algebra. That's associated with G and Q. And in particular, as we'll see, it has close connection to categorification of quantum groups. So the mirror of X is a hyperkähler manifold, which we'll call Y, which, to a first approximation, but not exactly, is obtained from X by hyperkähler rotation. Sorry, I went there the wrong way. So, more precisely, the mirror Y is also a moduli space of the exact same set of smooth monopoles, just on R2 times S1 instead of on R3, and where Y comes with a potential. Oops, I did it again. Have to be careful. So the potential is a multi-valued holomorphic function. Its multi-valuedness mirrors the T equivariant action on X. So if you turn off the T equivariant action, potential becomes single-valued. So the category of A-branes on Y can be thought of as, is an equivariant Rab-Fukaya-Sadel category, which we'll be able to solve explicitly. And this is done in this joint work with Danilenko, Li, Shende, and Zhou that appeared earlier this year. So in particular, we'll be able to identify the mirror of the tilting vector bundle of Bezrukovnikov and Kaladin. Now, unlike on the B side, where the tilting vector bundle is in general not explicitly known, on the A side, we'll be able to describe its mirror completely explicitly. Now, to begin with, it's helpful to observe that all the all the interesting information about the manifolds is contained in what I'll call their cores, which are half the size. So because we're working equivariantly with respect to the C star action that rotates the complex plane in R3, all the relevant information about the geometry of X is contained in the core locus, which I'll call the small x. That's a locus where all monopoles, whether they are singular or not, are at the origin of C and allowed to move along R. So now, while the small x embeds into the big X as a holomorphic Lagrangian, on the mirror side, the big Y, the Y fibers over the small y with holomorphic Lagrangian C star to the D fibers. So you actually get a pair of mirror symmetries, a downstairs mirror symmetry and the upstairs mirror symmetry, where the downstairs space is half the size. Now, a model example to keep in mind is to take the big X to be a resolution of an A-type surface singularity. That X is a moduli space of SO3 monopoles on R3, of a single SO3 monopole on R3, in presence of M singular ones. How many depends on which AMs. So for X, which is a resolution of the AM-1 surface singularity, its core looks like a collection of, P1s with a pair of infinite disks attached. Okay. The upstairs mirror is the moduli space, again, of a single SO3 monopole on R2 times S1 with potential. So the big Y is a C star fibration over an infinite cylinder with M marked points.
So your G is not Langlands dual in any way?
No, the G's does not, the Langlands duality does not enter mirror symmetry. G's are the same. Sorry. Not here because it's, not in this setting. So by SYZ mirror symmetry, the two cores share a common base, which is a real line with some number of special points. More generally, the downstairs space Y is the configuration space of points on an infinite cylinder, colored by simple roots of the Lie algebra, but otherwise indistinguishable. Those simple roots of the Lie algebra are one for each smooth monopole, whereas the marked points correspond to positions of singular monopoles. And those, again, will keep fixed, at least for the time being. So in the upstairs space, over every downstairs point, there's a C star fiber with a stop on one end. That stop comes from a fiberwise potential. So the categories of A-branes, both upstairs and downstairs, are finitely generated. The star here is for the fact that the generation here is not a theorem on the A side yet. It's not yet a theorem. Though there's, we believe it's true. So anyway, the generating brane downstairs is the direct sum of products of real line Lagrangians, defined as usual up to isotopy. Whoops. On Y, the upstairs space, the components of the upstairs generators fiber over the downstairs ones, with fibers which are real line Lagrangians, so one in each C star fiber. As a vector space, then the morphism algebra of these A-branes is generated by intersection points of the downstairs branes with coefficients and then the morphism algebra of the fibers. So thinking about the base, the intersection points in the base as Reeb chords, which are time one flows of quadratic Hamiltonian needed to infinities, you can get a graphic a representation of the intersection points. The algebra elements are just configurations of blue strings on a cylinder of unit height. The vertical direction parameterizes the Reeb flow, where the horizontal direction of the cylinder represents the S1 in the Riemann surface. So again, the blue strings encode the intersection point of the T-branes as a path from the bottom to the top of the cylinder, and the punctures get represented by these strings that are constant in time. So this is just the intersections in the base. In the fiber, then the morphism algebra of the fiber is just a polynomial algebra in D variables. D is just the total dimension of the base space. This is simply due to the fiber-wise potential. Okay. And so multiplying an intersection point in the base by an element of this polynomial algebra, you can represent it as by post-composing each of the blue strings with some number of dots. Now, one should be able to, this begs for describing the entire category of A-branes on the full space in terms of the category of A-branes downstairs with coefficients in the category of modules of this polynomial algebra.
How do you know this? You don't know infinite counting of triangles.
I will tell you exactly. This algebra can be. We can compute exactly what it says, and I'll tell you how we'll do it. So to compute the endomorphism algebra, we'll start not with the space we want, but with a space with certain divisors deleted. Okay. The deleted divisor has as its main components the diagonals, where any 2 points of the same color come together on the base. Okay. Now the two categories, one with and one without the divisor deleted, they have the same objects because they're both based on Lagrangians that avoid the diagonal. And correspondingly, the generators of Floer complexes will be the same as well. What changes is the algebra. Okay. So on the space with the diagonal deleted, we'll have the usual equivalence. So the category of A-branes is equivalent to a category of modules of some algebra, which we'll call A0. Okay. Now, that theory with the divisor deleted is very simple, because what we've done, we've deleted the diagonals in symmetric product. We've removed all the interesting curves. Okay. The endomorphism algebra is an ordinary associative algebra that's graded just by equivariant degree. And the equivariant degrees can be described as the sums of degrees of string bits. Now, so as I said, by deleting the diagonal, all the interesting maps that contribute to the algebra products have been deleted. And so what you're left with is just essentially one-dimensional maps, which are easy to count. There are no interesting maps of symmetric products. So the relations of this modified algebra state, so for example, this is just written for SU2, that the blue strings, the moving strings want to be taught, and then there are some few other relations. Now, the theory we really want is a deformation of this one, where we put back in the divisor we deleted. The deformation parameter is the instanton counting parameter that counts the intersection of maps with the diagonal. So again, as vector spaces, the algebra we want and the algebra, the naive one, are the same. So only the algebra structure will deform. How will it deform? So for SU2, so on general grounds, only the relations can deform. Okay. Because everything is in homological degree 0, you're bound to get an associative algebra. The only question is with which relations. So it turns out that to solve the entire theory requires counting a single non-trivial disk. For SU2, that single non-trivial disk will give you this deformation. Okay? In fact, you only need to check one of these because everything else is fixed by associativity. Okay? So you need to count. Counting disks by hand is painful. You have to count one disk. And not just for SU2, that single disk count turns out to suffice for all G, for all simply list Lie algebras. So that says the same. So for any G, the same strategy works of deleting the diagonal divisor and filling it back in. And so in fact, what you find with this with the single deformation, that if G is a simply list Lie algebra, the endomorphism algebra of these branes that I described is the cylindrical KLRW algebra. Okay, the same algebra we found on the V side. So the simple to formulate A-branes on the A side are mirrored into this direct summons of this mysterious tilting vector bundle. In fact, these KLRW algebras from the outset in the works of Kovanov and Lauda, they were phrased in terms of string diagrams. Now we know that these string diagrams are actual open strings that end on the T-branes on the A side. Okay. And they're physical. So this theorem that we proved establishes the other half of mirror symmetry once you can prove generation. So what's missing is to prove that the T-brane generators, the T-brane will actually generate on the A side as well, which we have no doubt, but we haven't written down the proof yet. So having found this new explicit family of examples of homological mirror symmetry, what else have we learned? Well, it turns out what you've learned is how to categorify quantum link invariants. So the categories of branes on both sides admit a braid group action. that comes from R matrices of the UQ quantum group. On the B side, a braid has a geometric interpretation as a path in complexified KLM moduli of X that avoids singularities. And in fact, the point and the complexified KLM moduli corresponds to a choice of punctures on this Riemann surface, which the mirror is based on. So because on the mirror, you can see the positions of punctures explicitly, on the mirror, the braid group action will be manifest and completely geometric. And we'll come back to that. But for now, just on the B side, the fact that there is not just a braid group action, but an affine braid group action on the category of coherent sheaves on X, which categorify the braid group representation coming from quantum groups, is a theorem by Bezrukovnikov and Okunkov. Mirror symmetry will make it manifest. Okay. Now, we want to categorify link invariants. So any link can be represented as a closure of some braid. To get invariance of a link, so you get this gives you invariance of a link as some special matrix elements of the braiding matrix. To categorify link invariants, what you need is objects of the category which describe collections of caps and cups that will close off braids into links. Now, it turns out that on the B side, X does contain such objects which have a simple geometric meaning. Okay? They, provided the representations you study are minuscule representations of G. So the brains you're after turn out to be structure sheaves of minuscule Grassmannians. Okay. So if you have some D caps, there'll be that many products of minuscule Grassmannians. Which minuscule Grassmannian will depend on the representation. Now, given the cap and cup brains, the Hom spaces between them up to braid group action necessarily have Euler characters, which are quantum link invariants, just given the theorem of Bezrukovnikov and Okunkov, where B here is the corresponding derived equivalence. Now, you can prove that the resulting, the Homs between the brains are actually not just have the right Euler characteristic that are link invariants, but that they are themselves link invariants. The proof is fairly abstract. It makes use of perverse filtration of that the category of coherent sheaves on X develops as near a wall in KLM moduli that corresponds to bringing two punctures together.
What are the two gradings? Like you have star star.
Aha. So one grading is the Q grading. Another grading is a homological grading. It has actually more gradings because you're studying links in R2 times S1. So there are additional gradings. But the most important gradings for us are the Q grading and the homological grading. So Webster in 2022 proved, in fact, that link invariants that come from the B side coincide with homological link invariants that he defined from KLR doubly algebras. And in fact, the nature of his proof is simply to show that then the morphism algebra of the tilting vector bundle is the KLR doubly algebra. Okay. So you know that you can prove on some geometric grounds that the category of B brains on the space gives you homological link invariants. And in fact, those are the same ones that come out of KLR doubly algebras from the 2013 work of Webster. All right, so we get link invariant. However, from what we've said so far, you get these link invariants only abstractly. In general, they're uncomputable other than for like products of unknowns. Okay. Now, it turns out you can actually solve the theory and obtain from it homological link invariants if you make use of homological mirror symmetry. Further use. So again, a helpful fact is that the brains of the upstairs series, whose morphisms we want to get link invariants, they all come from downstairs. What does this mean? The upstairs and the downstairs theories are related by pairs of adjoint functors. The downstairs theories will be easier to work with once you know from these pairs of adjoint functors which questions to ask. So every B-type brane on the upstairs space that's relevant to knot theory comes from a B-type brane downstairs via a functor that simply interprets the brane downstairs as a brane upstairs. And that functor has an adjoint. And the fact that adjoint functors exist means that you can recover harms of the upstairs theory from the downstairs theory, provided, harms of the branes of the upstairs theory that come from downstairs, provided one of these downstairs branes, you take it on a trip that send it first up and then back down. So we'll define, okay, this is maybe a bad name, but it's a name, the equivariant mirror of the upstairs X to be the ordinary mirror of its core. Okay.
But the core smooth, or they can have singularity?
The cores are very smooth. You saw even for the AN surface, it's very singular. on the B side. On the A side, they're smooth spaces, but the B side spaces are very singular. So equivariant homological mirror symmetry relating the upstairs X and the downstairs Y isn't an equivalence of categories. Rather, it's just a correspondence of objects and morphisms between them that come from these pairs of adjoint functors, and we'll make use of it. So recall our example of Y, which is equivariant mirror of X, which is AN surface. Mirror to ith vanishing P1 on X, on the downstairs X, is a Lagrangian, which is simply this interval brane. The functor that sends it straight up to the big Y simply pairs the downstairs brane with S1 fibers. And the functor that sends it down doesn't simply send the vanishing sphere upstairs to an interval brane. But computing the action of this functor either from Lagrangian correspondences or from mirror symmetry, you find a figure 8 brane. Okay. Just in the simple example. Now, in fact, for any simply laced Lie algebra, the branes that serve as caps and cups upstairs, which are these structure sheaves of minuscule Grassmannians, originates from vanishing cycle branes, which are these generalized intervals. It's an interval between two punctures, along which some number of colored points moves. Punctures that are labeled by a minuscule representation and its conjugate, and these colored points have to be ordered in a very specific way. The order in which you take the highest weight of one and lower it. Anyway, and as you send it back down, you get these generalized figure 8 branes. So we know harms between which branes we should study on the A side from mirror symmetry. So this equivariant mirror symmetry implies that harms between of the upstairs B side that gives us homological link invariants should equal the morphisms between the branes on the A side, the figure 8 branes and the interval branes. In fact, now that we're on the A side, where the description of braiding is completely geometric, you can, in fact, if you want to study knots, and you can simply proceed as follows. You take a link, project it to our Riemann surface, which is this infinite cylinder. You translate that link to a pair of A branes in steps. You first choose a bicoloring of the link, such that every link component has an equal number of red and blue segments, playing the funny game that the red always underpasses the blue. And then from a link, from a link, then you get a pair of matchings on the Riemann surface times R. From a link in Riemann surface times R, you get a pair of matchings on the Riemann surface. One colored red, the other blue. Where they meet, you place punctures. And finally, you associate to this a pair of A branes by replacing every red matching by an interval type brane and every blue matching by a figure 8 brane. And mirror symmetry implies that homological link invariants you're after should be Homs between the resulting A branes. So this is the picture that you get for SU2. The SU2 example is built on this AN surface. Remember, anyway. So the Euler characteristic of the resulting homology theory is, per definition, the equivariant intersection number of the A branes, where you count the intersection points, keeping track of gradings. Now, not just the Maslov grading, but also the equivariant grading. Now, the fact that that Euler characteristic is the quantum link invariant is guaranteed to hold by construction. The reason that this follows directly from Picard-Lefschetz theory, and the fact that what I call the equivariant central charge function, that's just the integral of a top holomorphic form times e to the minus w on your Lagrangian, is a close cousin of conformal blocks of the affine Lie algebra associated to G. These conformal blocks have similar integral formulation that came out of works of Shechtman and Varchenko, going back to Galfand school, indeed, and Fagin and Frankel, which differ from the actual equivariant central charge function by some insertions that don't modify monodromies. All right, so we are guaranteed that, we know this from mirror symmetry as well, but on the A side it's manifest that what you'll be categorifying is quantum link invariance. There's no mystery about what this thing categorifies. All right, so what we'd now like to do is to actually understand as Helm spaces. So a priori, they are cohomologies of the Floer differential. Now, rather than computing the action of the Floer differential by counting holomorphic curves, as you would need to by definition, and for which there's no general algorithm, having solved the theory, having understood homological mirror symmetry as well as we did, there's an alternate route to compute the Floer differential without counting any curves. So these braided cap branes, so these are figure 8 branes that you braid by moving positions of punctures on the Riemann surface around. They all come from upstairs, the images of the functor that sends the upstairs cap branes down. They turn out to have an explicit description in terms of that set of T branes. Whether or not they generate is something you have to prove, but the fact that these branes can be explicitly described in terms of those generating T branes that I talked about earlier, that you can show explicitly, because we'll actually know how to do it explicitly. So I'll tell you how. So again, these branes in the generating set, they'll generate the figure 8 branes, are all products of real line Lagrangians. In fact, the downstairs branes, they get equipped with a finite rank local system. It's not just the picture you see. The reason there's a finite rank local system as well, you have to really understand these branes as coming from images of the functor that sends them down. And the functor that sends it down doesn't just kill the brane in the fiber, which will be an infinite rank local system. It leaves a finite rank local system. Anyway, the downstairs endomorphism algebra turns out to be just a quotient of the upstairs endomorphism algebra by a two-sided ideal. We computed the upstairs endomorphism algebra. This one, the downstairs one, is just a quotient by a two-sided ideal. That ideal is setting the symmetric functions of those dots to 0. So symmetric functions of polynomials to 0. So it's a simple thing. So you get an equivalence of categories of the category of A branes downstairs and the derived category of modules of the endomorphism algebra of this T brane, which is equivalence with a star, admittedly. But anyway, we do know that the endomorphism algebra of the T branes, whether or not it can generate every single brane on site. So
your algebras are DG algebras, which kind of?
They're not DG algebras, they're associative algebras. There's no differential.
But you consider Hom in the derived category.
Oh yeah, well, because will describe our objects as complexes of the generators, and that's where the differentials come in. You'll see them. They're coming. Okay? So the algebra itself is just an associative algebra. Like if you study modules of a quiver, usually those quivers just have some arrows and maybe some potential, right? In the quiver itself, there's no differential. The differential comes later when you build complexes of modules of that thing, which we'll do. Hold on. I'll tell you how to do. This will be the first non-trivial explicit geometric example of a derived category I think most of you have ever seen. Okay. Other than the early examples are maybe Kovanov and Seidel. They worked a baby example, which is not a real example. These are real examples. And there are infinitely many. One for all simple Lie algebras. So these T-branes are projective modules for the endomorphism algebra. So by trying to describe these braided figure 8 branes as complexes of generators, you're looking for a projective resolution of the module that corresponds to that brane. Okay? So that complex will be a direct sum of generators in various degrees together with a differential. That differential is a degree 1 operator that squares to 0. Okay. So it maps the brane, the direct sum brane, to direct sum brane shifted in homological degree 1 by 1 that squares to 0. If you have such a description, so you can these braided figure 8s, we can describe them as complexes of these T-branes. It turns out you're done. Okay. For the purposes of hums we need to get link invariants. You're done because applying the hum factor, humming them with these I-branes, you get for free a complex of vector spaces. You don't have to do complexes, you get a complex of vector spaces. Whose cohomology you're after? Why is that true? The reason for the simplification is that these cup branes, in all cases, this picture is for SU2, in all cases, turn out to be Cazul dual to T-branes. So they are simple modules of the endomorphism algebra of the T-brane. So in other words, the only non-trivial hum for any T-brane to the I-brane is just from its exactly dual T-brane, and it's only in degree 0, cohomological and equivariant. Okay. These guys are cousins of thimbles, and so in some sense they are thimbles and dual thimbles. The reason they are cousins is that in this theory there are critical points at infinity, and it's a subtle theory if you really wanted to spell out the thimbles. Anyway, so the complex you get, so if you have a resolution of these figure 8 branes by T-branes, humming them with I-brane, you'll get a complex of vector spaces. That complex of vector spaces will be the Floer complex. Okay. The reason it will be the Floer complex is that two things are true. Firstly, per construction that I'll describe, the terms in the complex are in one-to-one correspondence with the intersection points of the original branes with the I-branes. Per this equivalence of categories, the cohomology is the Floer homology. So hence the differential has to be the Floer differential. So the identification of kth cohomology group of that complex is essentially the tautological consequence of having this projective resolution of the brane. And finding, okay, good. So once you know this resolution, you have the Floer differential without any further work. However, to find the resolution, well, you have to solve in principle two very, very difficult problems. The first problem is you need to compute which module of the endomorphism algebra does the brane you want correspond to. And once you know which module it corresponds to, you have to find the projective resolution of that module. The first problem is unpleasant. The second problem is unpleasant. In general, those are the kinds of problems that are solvable in principle but not in practice. Here, we can solve them in practice. Okay? Exactly. So what's happening here is that quantum link invariants are a solvable theory. From physics perspective, they come from Simon's theory, which is an exactly solvable theory, where most theories and quantum theories are not. Here, you find that miracle happening in geometry. We'll be able to solve problems because it has to do with quantum groups that you ordinarily can't solve. So here's what's going to happen. So we'll solve both of these problems at once because these cup branes that you'll braid are products of one-dimensional Lagrangians. So recall, if you have two one-dimensional Lagrangians that intersect over a point, you get for free a new one-dimensional Lagrangian by taking their connected sum at the intersection point. The one-dimensional Lagrangian you get by taking the connected sum is equivalent in the derived category to a complex which is the cone over the intersection point. And that works wonderfully in one dimension. So if the target is one-dimensional, taking cones it has a geometric interpretation as taking connected sums. So, for example, consider the cup brane in the SU2 theory. That's the one-dimensional theory here. We can recover that brane as a direct sum of the T branes by taking connected sums over their intersection points at infinities. Okay. So just by stretching the brane out, you can break it up into firstly, forgetting about what happens at infinity, into a direct sum of 4 components of the generator. And then you remember how it breaks at infinity. Each intersection point at infinity has definite equivariant and cohomological degree, and a definite name, and it's based on a definite element of your algebra, which you can just name. So to write the complex, you can start with any one of the T branes and record the harms you find as you go around. This pointer is pretty lousy. As you go around, writing down their name and shifting the degrees accordingly, which is an easy game to play. It's completely definite. There's other than the overall grading of the object, there's no ambiguity. Then you can organize so that you get a collection of the generating branes and maps between them. You organize the results by cohomological degree, and you find a complex that resolves as figure 8 with a differential that squares to 0. Now, you might be able to see, but probably not in the, actually this is mirrored to a structure. Okay, it's related to a complex that resolves a structure sheaf of P1 and T star P1, which is the B side. Anyway, now we need to do this for not just in one dimension, you need to do it in general dimension. So we'll start by describing complexes resolving the branes not on the space we want, but on a space with the diagonal removed. The divisor that corresponds to points of the same color coming together. So since all branes of interest are products of one-dimensional Lagrangians, working on y0, y where the diagonal is removed, you've killed everything but just one-dimensional maps to copies of A. So as a result, the complex that describes the brane of we want in Y with diagonal deleted is simply a product of one-dimensional complexes, up to gradings that you can keep track of. Okay, and these one-dimensional complexes, which you'll simply deduce from the construction, and as these one-dimensional complexes are easy to find, elementary to find. So geometrically, every map in the product complex is a cone over an intersection point that looks like this. Something non-trivial happens in one place, and then identity everywhere else. So in this way, the Lagrangian on the left is a cone over this kind of intersection point of branes on the right. So on y0, so which is y with diagonal deleted, it's elementary to write down the resulting complexes because there's products of one-dimensional complexes, and it's a simple game to play. You use the fact that the theory on the space you actually want is an h-bar deformation of the theory on the space with the diagonal deleted to find the complexes resolving the brane in the actual space. The reason this, there's no ambiguity in this H-bar deformation is equivariance. On the B side, you have in general, super strong equivariant action whose fixed points are isolated. There's no ambiguity whatsoever what you're going to get. The deformation is unique. So you get an algorithm that you can run for, in principle, arbitrarily complicated branes, arbitrary braiding, arbitrary G, starting with products of one-dimensional complexes that are elementary to write down, which per construction describe the brane on Y with the diagonal deleted, and then deforming to get a complex on the space you actually want. And there's a computer algorithm, which is joint work with Danilenko and Lepage, that's available on GitHub that does that. And gives you lots of homological algebra computations if you're interested in categories of any kinds of categories of branes on these spaces. Now, you can also get a more direct proof that this actually gives you homological invariants. So to prove these Hom spaces will give you link invariants, you need to prove that they satisfy Markov type moves. In our case, all those moves hold as a consequence of equivalences satisfied by these braided figure-8 branes. So the first move translates in the SU2 context to something like this, that you can just pass one figure-8 through another, and there's an analogous statement for any G. The stabilization move translates into equivalence of the left and the right-hand side, and then again there's an analogous statement for any G. Both of those follow from a single slide move that tells you that you can pass T branes through figure-8 branes. Okay. And again, there's an analogous statement for any G. Now, since we know explicit resolutions of branes on both sides in terms of the generators, proving this is just an exercise to show that you have homotopy equivalences of complexes. For SU2, you can just do this by hand. For more general Lie algebras, you want to use the computer program we've had, and we've checked this for a whole bunch of things, including non-simple laced algebras and so forth. Now, in the SU2 case, the theory that it produces Covenant homology. Now, the fact that it does is expected by a theorem that Webster proved back in 2013. It's not obvious that it would, but it reproduces it, including torsion. So, for example, for the trefoil, just by construction, you have to compute Homs between the following branes. And resolving this braided figure-8 brane and taking the Hom with the I brane, you just get a complex of vector spaces, as I promised you, with differential that you compute. That follows from the differential of the braided figure-8 brane. The complex you get is 18-dimensional, and you should compare it to a 30-dimensional complex that Covenant writes down. In fact, the same complex with C replaced with Z gives you Covenant homology, including torsion. Moreover, actually, the swiping move can be used to simplify this figure-8 brane to a much simpler one, because you're allowed to pass T branes through figure-8 branes. And then this much simpler picture gives you a complex that's only 6-dimensional, and with homology that's unchanged. So if you did this over Z, this is sort of the minimal complex you can possibly write down to get a correct homology of the trefoil. All right. So this theory extends to arbitrary simple Lie algebras as well as to Lie superalgebras. The story on the A side is essentially completely uniform. The B side involves, so for Lie superalgebras, the category of branes on the B side is not going to be a category of coherent sheaves anymore. It's going to be a category of matrix factorizations. And in fact, if you take G to be GL11, so as I said, on the A side, the story is completely uniform, is what I'm telling you. If you take G to be GL11, the category of A branes on Y, which is then just a symmetric product of this complex cylinder, is the theory that discovered by Oswald and Szabo in 2002. known as Heegard-Floer theory, which categorifies the Alexander polynomial. The categories we get for more general G should be viewed as generalizations of Heegard-Floer theory to arbitrary G. And they're all explicitly solvable, as I just told you. So this gives you a uniform approach to categorification of quantum link invariants for general Lie algebras. Thank you.
Just ignorant in the subject, but is it expected that one can give a definition at once for given links to define some for category to object?
No. So you really want to think of one single category. Will give you a whole bunch of link invariants. Anything that that you can get by plot closures.
What kind of Lagrangian goes to infinity in different ways? Yeah.
No, say this again. Sorry.
No, just different links should give Lagrangians if you go to infinity, and Holmes will be maybe some pairs of objects without doing any moves at all.
Can you say this again? I'm not following you.
Is it possible to define this categorified invariant, which is like graded space, as a home space in some a priori defined category between two objects without doing any moves?
In a category between two objects.
Some category in some two objects, yeah.
Well, I told you the story that I understand. And yeah, so
without doing moves.
Without doing any moves. You can start with a link, as I said, project it to this cylinder, and then discover the category that is without doing any moves. Yes, that you can do. Maybe that's not what you asked.
Do I understand correctly that the claim was made that the exponents of the central charges gives you filtration of the category?
Yes, that's right. Exactly. You can deduce it from that. Exactly.
Yeah. And did I miss that you constructed Lagrangians corresponding to minuscule?
Yes. Right. So if the representation is minuscule, then there's no ambiguity in constructing this Lagrangian, because essentially the ordering of the weights that you go from the highest weight to the lowest weight is just completely unique. If you, it's a good question. What happens in general? Well, we know a bunch of things. So caps and cops are examples of fusion products where two representations fuse to a trivial one. We know that there are branes that generalize more general fusion products. I don't know. If you ask me, can I categorify color Jones? I do not know. That's an example of non-minuscule representation. I don't know. I don't know. Well, I mean, this gives you a toolbox to ask millions of questions. Do we understand Jones-Wenzel projectors? I think this is a framework for doing things. And there are many, many, many questions one could ask. But I think the fact that this is the right framework for geometric framework for categorification of quantum link invariants is certain. How much can we do? I don't know. We'll see. We've studied true silence theory for how many years, right? Yeah. So what will come out? I don't know.
Maybe still another question. Should one stress that categorification of the vector space, which form kind of local system on space of links in a given link, right? Not just isomorphism plus, but a local system of. Because that will be natural. Yeah, you check the space as isomorphic, but not canonically. I don't know. Maybe one question one can ask if one can understand homotopies between distinct lengths. Yes, no. I think on general grounds you expect to be able to do this in the context of the A model. The question is, can you actually explicitly construct them like as maps? That should be a local system.
Yes.
System space of links is given actual geometric links.
Right.
Questions?
Yes, why do do we meet Heidegger-Floer theory only once?
Why do we meet Heidegger-Floer theory only once? Well, in some sense, you should think of Heidegger-Floer theory as being the beginning. I wanted to, and in many places, the way I tell the story starts with Heidegger-Floer theory. I wanted to tell a different story here. But yes, the A side is essentially a generalization of Heidegger-Floer theory.
Any more questions?
So, here we are working with the character varieties with the space of with the specific ADA triggers because they're interested in representation theory. But would you, the mirror symmetry statements, I assume, would be valid with the greater generality?
If you replace the
even cluster varieties, or
you can certainly that's right. You can certainly consider arbitrary quivers and get analogous statement. In fact, quiver-Hecke algebra is kind of meant to be, I think, starting with an arbitrary quiver. Yeah. So it's possible that existence of loops makes the story less geometric. It's less geometric in my mind. So quivers with self-loops might be a little more complicated, but I mean, in principle, yes. You won't get link invariants, but I think the story of mirror symmetry should proceed. Yes, that's true.
You mentioned that simply laced only. What's the problem with?
Oh no, there's no problem. So okay, good. To get non-simply laced Lie algebras, you want to use folding. Now on the A side, you just write down the space. It turns out on the B side, it's a more interesting story. You fold the simply laced quiver of a Langlands dual type, and then extract the correct piece from it. That will give you the non-simply laced scalar double algebra that matches the A side. So it's some kind of to me, it's a novel mirror symmetry statement. It's not obvious why this was the right question on the B side. I don't know how to put it in the usual framework of mirror symmetry. Okay, we delete the divisor, turn on the potential, and so forth, like these kinds of things. So it's slightly novel on the B side. But the fact that the fact that it's true, it's going to be a theorem, and we just haven't written it up yet. So.
Yeah, sorry, can you say anything about closed manifolds?
About what?
Closed manifolds?
Great. That's a great question. It turns out that the story has an extension to Verma representations. So not just finite dimensional representations, but Verma modules. And that, right, great. So there, we know which questions should one ask, but I'm not in as good of a situation of saying, okay, I know how to answer it. So this would give you invariants of not complements. I can't say much. So I can tell you which Landau-Gisbrook theory you should study to get invariants of braids in not complements. Okay. Then you should be able to fill them. Yeah. So.
Yeah.
Verma was arbitrary weight, so yeah.
Sorry?
Verma was arbitrary highest weight.
Well, with generic, so start with just generic highest weights, like corresponding to say full punctures and Davides theories. But you can generalize this to some. There's no restriction about what you.
More questions? Well, if there are no more questions, thanks again.